All right. Good afternoon, everyone, or good morning to those who just started their day. And thank you so much for joining our technical webinar this afternoon. We are so glad to have you here. And we are going to start now. Hopefully, everyone is ready. All right. So, first, before we begin, let's go ahead and switch off the notifications on our screen so that it won't be distracting you from the webinar later. So please go to the settings icon right beside the purple one on your lower right hand corner, and under the notification settings, please make sure that the boxes are not checked or they are blank to make sure that no notifications will be going on your screen later on. Could you please give me a thumbs up or an okay when you're done? All right, thank you so much for that. I see a lot of people had already done it. Great. All right, let's now proceed. For those who haven't done so, please continue. All right, so I'd like to welcome you to our authentication for remote critical infrastructure IT/OT assets technical webinar today, and it will be presented to us by Professor Zubair Baig, and he is our lecturer at EIT. And before anything else, I would like to remind everyone that if you are wondering about, there will be a video recording or a copy of the PDF slides. Yes, we will be sending that within the next 2 business days through email. Okay, so please make sure that you monitor your junk folder as well to make sure that you receive the recording and the PDF. And there will be a certificate of attendance. There is no charge, it is for free. However, it is only digital. We don't print out and send them to you. And of course, that will only be given when you complete this particular session. And let's talk a little bit about EIT. So we are dedicated to ensuring that you receive a world-class education and for you to also gain skills that you can immediately use in the workforce as an engineer or as someone who is practicing engineering. And we are an engineering specialist. We are one of the very few institutes in the world who specialize in engineering, and we deliver a variety of courses. We have professional certificates, diplomas, advanced diplomas, undergraduate certificate, graduate certificates, bachelor's and master's degree programs, and a Doctor of Engineering program as well. We are industry oriented when it comes to our programs because they are designed by industry experts, just like our presenter. He is one of the industry experts that would contribute as well to the lessons and, of course, the success of our programs. And that is to ensure that our graduates will have cutting edge skills and so that they would be valued by their employers as well. And our content remains current with the rapidly changing technology and industry developments. When it comes to accreditation, we have both the Australian government and world-class accreditation as well. So with the world-class accreditation that comes with Engineers Australia, under the different international engineering accords, which are the Dublin Accord, the Sydney Accord, and we also have the Washington Accord. And as mentioned earlier, we have industry experience lecturers, and they are not just lecturers, but highly experienced engineers and subject specialists. And they have a lot of applied knowledge in this space. And we also have technologies that we employ at EIT for both online and on-campus courses, and that enables us to source our lecturers from a large global pool of expertise. And we also have a unique delivery model. So our programs are delivered via a unique methodology that make use of live and interactive webinars and international pool of expert lecturers. We also have our dedicated learning support officers, and they would help our students with anything that is related to their studies so that we would ensure that they have a smooth learning experience here at EIT. And of course, I'd like to mention our state of the art, um, such as our hands on workshops and remote laboratories and simulation software. So, those are our state of the art tools and materials that we provide our students. All right, so that's all about EIT. And I would now be letting Professor Zubair to introduce himself to us and present the topic for today. Thank you so much.
Thank you, Lisa. I'm Zubair Beg, and I'm very happy to be here as part of the EIT community to share some of our research findings in a very interesting topic, which I shall refer to. At the moment, I'm an associate professor in cybersecurity at Deakin University. Love to work for EIT, but I, I'm not affiliated to EIT. I'm a guest speaker for EIT today. I also had research translation in cybersecurity at the Strategic Center for Cyber Resilience and Trust at Deakin University. Co-authored quite a few journal papers, conference papers, the typical load and academic experiences is what I have here. So I wouldn't be bragging about it, but it's just something that's been done over the years, primarily in the cybersecurity um, space, and which has been a very good experience because I should be able to talk about diverse problem domains and be able to share some of the experiences that we have as researchers, not simply across cybersecurity for the internet, but also across the Internet of Things and industrial Internet of Things for that matter, which is the topic for today's talk and so on. So we bring together in a bespoke manner various domains, various disciplines. We adopt artificial intelligence based techniques to solve our problems and other solutions as well. So that's where I'm at briefly, and you can reach me just doing a Google search of my name. I should be able to be noticed, and you can pick my email address and should be able to contact me if you've got any questions or you wish to chat about anything cybersecurity. So this is where we are at, and this topic is very interesting, very apt in 2023 and beyond. We're in an era where the industry, which evolved from traditional mechanical devices that were used for manufacturing at the turn of last century, were automated through the introduction of electrical gadgets and devices. And from there on, through digitization and through the introduction of computers and subsequent miniaturization of computers and easy access, availability, and affordability of computing devices, took us to a point where we could automate beyond um, very basic calculations. So we should be able to, for example, the figure to the left tells you that if you have a water treatment facility, traditionally you will have flow of water, and that entails raw water coming in through a pipeline, getting stored in a water tank, for instance. And if you can see here, that's a water tank, raw water coming in, and that's a water tank where it could be stored. It could be pumped mechanically, and it could be subsequently dosed with chemicals to clean and filter it. That's a dosing process. That's the level of filtration called ultrafiltration. And you would want to dechlorinate the water before you would be able to use it. There are techniques out there, physics again, reverse osmosis, for instance, and permeation, and the other things that come with the treatment of water are adopted here. So it's a six-stage process, and you end up with clean water that could be potable and used by us. So you can see all these red dots over here. It's just a cycle of events that take place and processes that take place for water treatment facility. But we can introduce electrical engineering. We can introduce devices such as a programmable logical controller, which automatically is able to open or shut a valve, or is able to control the pressure with which the water is flowing, and is able to transmit it to a unit in digital format, which is ones and zeros. So that is subsequently processed, and you can take decisions based on those numbers. So this is digitization to the right, and this is operations technology to the left. So, so that's OT, and this is IT. And combined together, IT plus OT is what leads us to the future of manufacturing and the future of the industrial revolution, in the sense that this is Industry 4.0, combining digitization with mechanical devices, with electrical devices as well, right? So this is where we are at. And I'm talking about very involved science here, very involved engineering of a solution. But if you wear the hat of a person who wants to make sure that this facility is not disrupted, or this water treatment plant is not impacted by the acts of various malicious um, threat actors that exist out there and that have been causing menace because they want to disrupt routine activity, cause harm, to gain some sort of a market advantage, for instance, or to be able to bring down a facility and cause harm to a city. And these actors do exist out there. And there are numbers that tell us that threat actors do exist. And particularly for the industrial Internet of Things, because of the fact that these devices have not been designed with security in mind, the chances of it being impacted through a cyber attack are very high. Well, that's why I'm here to talk to you about some of the associated research. So very basic challenges. Now, if you could do a Google search, identify some of the challenges, then you will come up with a list, which is a very common list, and all the vendors and security solution providers will talk about the same list, like segmentation of the network, filtering network traffic, talking about firewalls, access control policies, safeguarding data through encryption, checking integrity, and those standard features. But from a holistic viewpoint, if I were to tell you what the challenges are the fact that there are a lot of stages in these processes and they're interconnected in nature. They're complex. I've got like 20 different sub-processes in here. Each of those have got a physical background and a chemical explanation to it. And it's got a device like a valve or a motor or a pump of some sort coming out from a manufacturer which is not known to us. It's not always Siemens. It's not always Hitachi. It could be somebody else who's produced a device, which is handy, cost effective. I've got a manufacturing plant. I would go ahead and procure the device, and it will help me dose chemicals as part of process P2 in the water treatment facility. Right, so it's complex. So you're talking about 1,000 permutations here. Connectivity is another thing. And all of these expose vulnerabilities of the system, the OT-IT integrated system, to a range of security threats. And these threats, some of those could be very serious, and the likelihood of those occurring could be very, very high on a scale of 0 to 10. And some of those could be less likely to occur. But at the same time, those are threats that if they do occur, they can shut down an entire process, right? So you can cripple an entire network through a cyber attack. And one of the big factors there is a human factor, because human beings, us, we tend to be the key exposure point for a lot of major security events that take place across various domains. I've clicked a link. I wasn't too sure whether it was a legitimate link, and I was able to download malware on a device that is connected to a programmable logical controller of the treatment plant. What do? I'm responsible, but I wouldn't claim responsibility because I just made a mistake. Now, who is responsible for it? It's probably the organization which wasn't effective enough in rendering training to human subjects who were handling a process or a digital device connected to a process in there and so on. So these are challenges, and they exist, and it's only going to get worse because we will have not all systems as being 6-stage processes. We may have 66 stages of processes, and multiply that with 3 devices at each stage. So that's 200 plus various types of devices. And if it's coming out from various different types of manufacturers where you wouldn't be fully aware of the device firmware, what is the hardware specification of the device, and what language does it speak, or the protocol that it uses to communicate with another device. So if I open up the box, there are many, many complications beneath the surface. And what I'm showing you here is a bird's eye view of what the security problem is for this type of a scenario. And is this hypothetical? Absolutely not. Industrial control systems in a critical infrastructure, if you look at the numbers, I'm talking about 5 years ago. So this was a major experiment conducted at the Rochester Institute of Technology. Collected 988 data samples out of surveys of manufacturing plants and stakeholders associated. And they had identified the industrial control system components as being the most vulnerable, as being the human-machine interfaces that allows you to try to handheld devices that you can plug in to, say, a PLC to configure or reconfigure it, or a device you could plug into a smart electricity meter of a household to be able to pick up electricity readings for a month of electricity usage, or SCADA devices, which are supervisory control and acquisition devices, or programmable logical controllers. So these were the key vulnerable points of exposure of an industrial control system. What percentages of ISIS vulnerabilities had an architectural root cause? 63% roughly, because products were not designed with security in mind. So firmware is very exposed. It's like building a house, but keeping the door open because the lock was not invented, and anybody can just walk in through the front door, right? So that's what it is. That's the analogy. What are the most common architectural weaknesses for industrial control systems? Improper input validation. Inputs coming in, I'm a water pump, I'm not validating the instructions received. I'm just executing those as is. So that's exposure of vulnerabilities. Weak authentication, anybody can just walk up to a smart electricity meter. It's not going to authenticate the human subject, and anybody should be able to read the electricity readings for a household if there isn't authentication in place. And access control. So users are not authenticated, and a baseline user can be operating as a manager. So that's for escalating privileges. And 24% of architectural weaknesses were identified as being through weak authentication and access control. And which were the most often compromised? These were it, right? So to split those up. So that's where we are at. So let's look at some further errors if the slide loads. It's a bit of a delay in loading the slide on my side of things. There we go. Now, if you look at the stats here, now this is very recent. This is coming out of a few weeks ago. This Kaspersky did identify a couple of attacks as being the most popular attacks against industrial control systems this year. The first one being deny listing. And deny listing is where you would have a list of people who are barred entry into your network, and anybody else is let in. Because deny listing is very limited because that list is not exhaustive, and therefore I was allowing people to penetrate the network, whereas they should not have been doing so in the first place. So that was the number one attack, not a threat, an actual attack. And the second one was malware. Just clicking a link, downloading a piece of software which corrupts the firmware of a digital device in the industrial IoT platform and causes disruption to processes. The third being phishing. So malware and phishing go hand in hand. Phishing is where you would lure a legit user to access a website through which a piece of bad software, like malware, is downloadable. And the other thing was traditionally safer regions, like most of the Western countries, were reported as now being vulnerable. Although Africa still remains the highest victim percentage at 40.3, but these countries are also catching up. And billing automation systems, it's also an industrial IoT system, was the prime target. And at 38% of the attacks against it. Energy sector also saw an increase of roughly 36% of attacks. So those are numbers coming out. The red bars here are basically indicating the first half of 2023, which is this year, when the attacks are simply going up. So let's quickly look at threats and vulnerabilities. Again, from a higher level viewpoint, industrial IoT in the mining sector is very popular. You know, these huge trucks with tires the size of a building that are, you know, deployed here, even in Perth and in Western Australia, for that matter, in the Pilbara region, for instance. They're automated. A lot of them are operated remotely, so you don't have to be behind the wheels to be able to drive that truck very deep into a mine pit to be able to excavate and pull out minerals and bring those back to the surface. So those are automated. They're driven by remote control, just like kids would drive a very small car using uh, a remote control device, right? So that's happening now. Even drones are controlled with remotes, obviously, through a ground controller. So in the mining sector, industrial IoT exposure is cyber espionage because there's a lot of money in mining, and you would have secrets stolen as to where the mining site is, and so on. Phishing attacks I've mentioned, inadvertent clicking of links taking you to bad websites, and third-party access. Access by a contractor who's been given privilege to use a human-machine interface handheld device and be able to configure and reconfigure a PLC. In manufacturing, malware, ransomware, which is a type of malware, which data is encrypted and you have to pay an amount in usually bitcoins before you can get it back. Distributed denial of service, where a large volume of network traffic is launched by the adversary towards a single target. Could be an OT pump to pump water, which is connected through a digital device, a logical controller that's controlling the water pump, for instance. And trust me, you don't need a lot of messages or useless packets to be able to cripple that type of a system, as opposed to the internet, which is a lot harder, but again, which is very popular up there. A variant of a phishing attack is a spear phishing attack. Again, luring legit users to make their way to a malicious website. Hacking the device itself, not too difficult. If there isn't sufficient authentication in place, you can penetrate a device by guessing the right password, if at all there is a password. And then there is legacy system vulnerabilities, traditional systems that are not designed with security in mind, integrated with existing pumps, integrated with existing declaration devices, and so on. IIoT for the smart electricity grid will have similar types of attacks, including attacks that are persistent, complicated, and they want to lurk in the background to be able to stay there for a longer period of time, to gather activity around an electricity distribution plant for a very long period of time. In healthcare as well, we've got various types of attacks. So these are threats against each of those critical infrastructure, industrial, IoT plants. And if you were to look at vulnerabilities or entry points to each of those systems, I'd mentioned previously that the protocol that is adopted for communicating is not entirely secure. There are protocols in place such as Modbus and Profibus that do not enable like secure HTTP type traffic or transport layer security type traffic. And therefore, these communication protocols are allowing these IoT devices to talk to each other in plain text without validating the integrity of messages exchanged and without any authenticity of the messages in the first place. So the protocols are inherently insecure. There is not sufficient authentication and protection of data. And by design, any industrial IoT application will have vulnerabilities, which were not patched in the first place. Monitoring of security, like a firewall or a security control, like an intrusion detector that is able to pick signals that represent any of those attacks from the previous slide, may not necessarily be there because it's not necessary. Security generally is an afterthought, so you tend to deploy control only after you've been targeted in a cyber attack, and even then a lot of people still wouldn't do it because they wouldn't know where to deploy the security control at, right? So that's an issue. Other issues could include disabled logging in firewalls and routers, so you wouldn't know what's going on. You don't want to log everything that's going through your network security control because that's a lot of data to deal with. So you would just flush it at the end of the day because there is no security policy in place, right? There's less governance. There is no plan to recover from a disaster, and therefore there is a lack of attack detection, and there is unsecured authentication. There is no encryption on PLCs because that's an expensive operation, and that slows down the processing capability of a PLC. And finally, there's lack of identity management. So all in all of these things go hand in hand, but there's poor governance. There is no attention paid to the risk, and if there isn't much attention paid to the risk posed to the IT OT platform, So you wouldn't be bothered about providing a solution in the first place, right? Until you're hit by a cyber attack and then it goes back. So it's a chicken and egg thing. And that's how typically technologies are adopted with no security in mind, and then little security and a lot of security later on. If and by that time the technology becomes obsolete and it gets replaced with something else. So architectural weaknesses in ICs, I wouldn't go into the finer details here, but if you look at it very carefully in the slide we're talking about, these are common vulnerabilities and exploits published on the internet against industrial control systems. So if you see the frequency of occurrence, improper authentication, improper access control, like usernames, passwords are not validated correctly, or a baseline user operates like a manager, these are pretty high. Use of hard-coded credentials, like default usernames and passwords, this is also very high, and so on. So a lot of these are to do with input validation, authenticity of users who are fiddling around with these devices and so on. Interesting numbers here, and these are actual numbers. Um, Getting into the security by design issue, so we don't have security by design in any of these architectures. So we consider a typical industrial control system. For those of you who are electrical engineering savvy or have got a background in computer engineering would know what I'm talking about. So you have sensors and actuators. Those are the field devices, right? They sense temperature variation or pressure variation, the depth of water in a water tank, for instance. And then there are control systems. Control systems are the programmable logic. You program them and they control the speed with which a motor rotates or a valve opens and shuts, frequency at which it's happening, and so on. So these are control devices. And then there is supervised data acquisition devices and human machine interfaces, which are fed with data coming in from PLCs to operate on it, right? And these PLCs could be substituted with a smart electricity grid. You still have an HMI for being able to pick those data items and information from the smart electricity grids. And then finally, it goes to a very thick backend cloud system for storage and further processing. The protocols that are operating here, Modbus, which is built upon the TCP standard, um, telemetry protocol, which is MQTT, HTTP from the internet. At the physical layer, it's either Wi-Fi or the Ethernet. So you see, there is a big variation in the protocols at each of those stages. Communication is achieved through one of these protocols. Security has to be customized because each protocol is different. Each language is different. Packet sizes are not static. And there is varied transmission rules and reliability. Like a PLC would establish a connection with SCADA. Probably not. It's just going to be a poll message coming in, and a PLC would just dump a response to it, not paying any attention to the matter of that message being vaporizing in transit between these two uh, device types. Specific communication requirements that facilitate effective communication don't exist. So if you look at this, it's a simple figure, but it's very complicated when it comes to security. It's simply not there because we can't be bothered about the various languages that these devices speak and how this could be overlaid with some type of robust security solution. Another example of an architecture here is a smart electricity grid. So if you look at the this is not the transmission end. This is rather its neighborhood area network and the home area network. So this is a household with a smart electricity meter, solar panels and the likes, and all these devices connected to it. Probably an EV would be there these days. It wouldn't have been when I first came up with this figure. And that's the home area network, lots of households. There's a data concentrator unit. It collects the data and it goes through a digital channel for further processing in a central entity. Right. So that's another architecture that you can consider. Again, with no security solution in place, because we don't know what protocol is in place here and how these devices are communicating with each other. Even if we do, it's complicated because smart meter to DCU is different from a DCU to central entity here, which is processing that. So I looked at very quickly a couple of high-level examples for architectures. And if you want to look at the attack models from the previous example on smart meters, then the compromised smart meter may be reporting incorrect readings to peer meters or even to the data concentrator unit, right? So this is a rogue meter. Why is it rogue? Maybe HMI. Let me just use the brush here. So let's see if this works. All right, so the HMI here, this is lousy. But anyway, I'm not a really good artist. Yeah, okay. HMI was used, that's a human machine interface. It's a handheld device to inject malware onto the smart meter because there wasn't authentication or credential validation mechanisms in place to prevent this from happening. And now it starts misbehaving. So a simple security solution in place here would have made it a little bit harder for the adversary to be able to make changes to the firmware or to reconfigure or misconfigure the smart meter, right? So that's a typical attack. Now, another type of attack, if you look at it very carefully here, now this is a little bit more involved for those of you who are interested in algorithms, where typically the attacker would start off with reconnaissance. They would try to sniff and figure out where is the smart meter that does not have authentication in place, or where is the process in the water treatment plant that has got a PLC which is ready to accept any downloads without validation, right? So that's reconnaissance. And then you can use a tool. Sometimes we do use a cybersecurity tool, Nmap, to pull up a list of all those networking ports and protocols that could be targeted. So this is planning for an attack. And then you can carry out an actual attack, which is to flood the network or to reconfigure the PLC memory and so on. If you have a security control in place, we can capture that traffic and pull up a signal that would help us raise an alarm. If you don't have that in place, then we are in trouble. So there is no authentication here, nor is there any authentication here. And we're letting the adversary do and go about its business of charting out the entire network topology through these types of activities. And this is quite possible, and it does happen. It's happening as we speak, especially against industrial IoT, because that's where the damage done could be very significant. And you could do mapping. So that's a systematic way of understanding what's going on from a cybersecurity perspective. So some of the things that we do usually is we map. So we pick up standards. Like the Mutter standard is a very common standard for mapping stages of an attack against techniques that an attacker can adopt, against specific details that will lead us to charting out a plan as to what needs to be done next to ensure or to overlay security for any of those processes in an OT plant. So this is what helps us do it. If we can't enumerate all of this, then we wouldn't know where to start out with a security solution. So that's a typical example of how security solutions can be built for these openly exposed systems. And then these are some of the other finer details that you've recently published, where, for example, IP addresses, the rogue IP addresses, or IP addresses that belong to uh, entities that exist in the dark web, or that those are entities that exist outside our network. I could list them in the denial list. So I would prevent them from accessing any of my devices. It's a very simple control, but it's just like shutting the door, except if somebody you know who belongs within the household is allowed to enter the household, and everybody else is just repelled. Very simple control, very effective. And there are further details on how this could be impacted. Like if you know the addresses of the attacker, you can configure the security control to help you with it. You can specify protocol type and relevance for security analysis as well. And that will help you pick up whether the significance of enabling a security control is high or low. If it's low, that means the likelihood of this type of an attack is low. So you would keep it on the back burner for now, and you wouldn't be bothered about enabling a security control anytime in the future. But it may become medium or high, at which point in time you would revisit that situation. But the high impact ones are the ones that are, the chances of them occurring are pretty high. So you have to address those security threats as soon as you possibly can. So let's look briefly at authentication. As I mentioned, that's one of the key issues. Even the statistics tell the same story. Now, this is a typical example of an OT, remote OT facility, and you've got a human machine interface, SCADA system, PLCs, and RDs. This is a human user, and the human user is denied access to this machine because there is a connection disruption preventing this remote mining facility from being able to connect to the core enterprise network. So this could be, for instance, Perth, and this could be the Pilbara. And there's a disconnection. So this human user walks into the facility to make some changes or fixing the devices, and it's not able to log in. So there was a security solution in place, but it's not working. So one of the solutions that we'd worked out here as part of the research team that I was leading was to enable this entity, this human being, to still be able to authenticate itself to these devices in the absence of a network connection. Right? Complex problem, but you can solve it through application. So that's a typical architecture of what we're talking about. That's the corporate headquarters with the cloud devices and firewalls and the likes. And then that's a plant zone. You'll have a bunch of devices that are servers, again, digital devices. And then there is a functional element here. There you've got these field devices, including control systems and other OT devices, cranes, robot arms, and so on. At the same time, they're interconnected via the IT devices to these central facilities. So again, it's just reiterating the complexity of the nature of this job. And to enable a security solution requires us to have knowledge of these various devices and the protocols that they usually follow for conversations and the likes. And only then comes a security solution. A simple solution that we worked at, this was a little bit older than the more recent solution that we've worked, but some of the things that we work on include very basic communication hardening. In this case, entity A wants to speak securely with entity B. So the messages exchanged could comprise a plain text message concatenated with a temporary value, we call it a counter. And we can encrypt the whole thing with a key, a shared secret key for encrypting this. And this shared secret is between these two entities. And then for integrity validation, we could do generation of a message authentication code. For those of you who are aware with hash value calculations, this ensures that if there is any transit error in communication or a message was deliberately dropped or disrupted by the adversary, you should be able to pick any changes to it through calculation of a message authentication. It's a fixed size message, digest, encrypted. There's a message digest of a very large message, arbitrary length message, into fixed length size, and it's digested, and then it's encrypted. So these are a couple of very simple mechanisms, and these are adopted in various flavors across any two devices that wish to mutually secure a channel that they're using for talking to each other. And then we came up with more complex solutions. I wouldn't get into the details, but nevertheless, we were able to consolidate keyless authentication into just FIDO2, transport layer security, public key infrastructures, multi-factor, CTAP, token-based, and we were able to incorporate that whilst adhering to an international standard for industrial control systems, which is the Purdue model. And we came up with a very complex test bed where we were able to build a solution to enable human to device mutual authentication. And we were able to do that successfully. So I'll just walk past this slide. But then here is a summary. So cyber attacks are rapidly rising, and more so in the industrial IoT space of things because of the commonly use of word digital transformation. So I would call it digitization of the OT space, digitization of the industry. Standards are heterogeneous, thousands of families of devices working in tandem. Industry is different from one point and one angle to the other. There are issues with compliance, there are issues with non-compliance and financial or reputation damage. And automated threat modeling and generative AI just makes it difficult because the adversary can pull up a threat vector which is 0-day in the sense that it wasn't seen or heard of previously. Lack of policing, and finally, you don't need to have knowledge of how the attacker models the threat to be able to do so. And that leads to zero trust. And that also leads to zero trust architectures where you want to authenticate and re-authenticate to an entity because you don't trust a person beyond a certain number of hours, minutes, or milliseconds, or even microseconds. So that's zero trust architectures. And that's where the future lies. So you go against threats, but you stay ahead. That's the ideal situation. And we persevere in doing so as the cyber cops. At this point, I wish to thank you for being patient with me, and I'm pretty sure there will be several questions that you may have. So I'll be hanging around for some time to take your questions. So thank you for attending.
Thank you so much, Professor Zubair, for that a very informative presentation.
Thank you.
Um, do the others have questions about the topic that we have? Okay. While you are preparing yourselves with your questions, I would like to go ahead and let you know about our upcoming courses, which are the Graduate Diploma of Engineering in Electrical Systems, Online Master of Engineering in Electrical Systems, which are both starting on the 2nd of January, which is next year. And please stay tuned as well because I'll be posting the QR code for your certificate of attendance shortly. And we also have our professional certificate of competency in substation design main equipment on the 16th of January. And on the same date, we also have our advanced diploma of electrical and instrumentation engineering for oil and gas facilities and professional certificate of competency in hydrogen energy production, delivery, storage, and use. And we have the professional certificate of competency in industrial Internet of Things on the 23rd of January, which is very relevant to our topic for today. And a lot more courses coming in February that are related to electrical engineering, right? And we also have our upcoming webinars in here. So just go to our events page for you to be able to see our upcoming webinars. So we have our, there are 4 of them here. And this is our QR code that you can scan for your certificate of attendance. And I will also be posting this link for you to be able to request for your certificate of attendance. And please make sure that you request or you really make a request for your certificate, because it won't be automatically sent to you if you don't request for it. And please do so on or before Sunday afternoon, because Sunday afternoon is our cutoff for requesting for certificates, so that we can go ahead and prepare them for you. And most probably by Monday or Tuesday next week, we will be sending out your certificate of attendance to your emails. And I am posting the link here in the chat. You can use that as well. There's one question here, but hold on. Right. Yeah. Professor Zubair, I have one question here from Russell Vincent Torres. Were you able to answer this already?
Oh, yes. So the question for Russell is around the CM solutions. Yes, so CM is monitoring for incidents, and cybersecurity comes in various modules and flavors. So monitoring is definitely a very important aspect of cybersecurity. So if you can't monitor, then you wouldn't be able to pick up what's going on, which is not right, and where could you improve. So monitoring is one thing. Preventing the attempts by the attacker to get in is intrusion prevention or detection. That should go hand in hand with CM. Firewalls is another thing. Segmenting the network to separate the sensitive areas of your computer network from the less sensitive areas, a very popular topic and a common security control. And then there are authentication, authorization solutions, multi-factor authentication solutions, and the likes. So if you look at the security solution landscape, and you can even refer to the NIST NIST standard for OT security, and they'll be talking about all these various components, including CM, and how they work in tandem to be able to address the security goals. So yeah, so that's my answer to your question, Russell.
All right. Thank you so much. And we don't have much questions today from the crowd, but for those who have further questions and maybe you would think of that question later on, or maybe you're not that comfortable posting your questions here, you can always send an email to webinars@eit.edu.au, and we will be forwarding that to Professor Zubair. You can also visit our website, which is www.eit.edu.au, and we also have our phone numbers here for those calling from outside Australia or inside Australia. And for you to view our list of courses that we offer with their intake dates, you can go to www.eit.edu.au/schedule. Right? I am going to post a certificate link again here. And I'll go ahead and sorry, I'll go ahead and stay for like a few more minutes, and then I will go ahead and close this webinar. So thank you so much, everyone, for participating today. And again, feel free to send us an email if you have more questions. And we are very glad to have you here and hope to see you in our next technical webinar sessions. And thank you so much as well, Professor Zubair. Have a great day, everyone.
All right. Thanks, everyone. Thanks, Lisa. Bye.